Good afternoon, everybody. I hope that lunch wasn't too good and you're going to pay some attention to an exciting topic that I'm going to tell you about. This is the obligatory information as to where the money came from. Most of it came from this program. I'm sorry, it's flipping over on the laser. So this program is paying for most of what you see today, and there have been some previous programs, but this is the primary one, and we are certainly grateful to NASA for giving us the resources to continue this project, which is entitled Iodine RF Ion Thruster Development. And I will tell you why iodine. I will tell you all about ion thrusters, probably more than you ever want to know or ever heard of. Here is my name. I'm the president of the company, and the guy that's actually doing all the work, his name is Michael Tsay. He's a young PhD from MIT and extremely bright and capable fellow, and he pushed this project quite far along. So okay, well, there's such a delay in this feedback that you never know if you have to push it again or not. Slide up on there now is the requested information on the company. We were founded in 1985, roughly 50 engineers with some support staff of the order of $10 million revenues annually. And we are the conventional small business, not women-owned, not veteran-owned, just small business. Our core business is spacecraft electric propulsion. The flagship product out of the company are Hall thrusters. And we have the distinction, or at least claim the distinction, that all Hall thrusters that are flying or have been built in the United States have a heritage to our patents and to our licensing. We make electrospray thrusters, pulse plasma thrusters, gridded ion RF thrusters, and that's what you're going to hear about today. We also make small green monoprop, or something different than hydrazine, which is getting to be extremely important these days. We make, starting to build various space systems, such as debris removal systems for space debris mitigation. And last but not least, we are endeavoring for quite a few years now to develop high specific impulse propulsion for CubeSats. You will not find us offering cold gas thrusters. That's not our specialty. We will be always focusing on the more demanding, more sophisticated electric propulsion for CubeSats that can actually get you to places where some of the more demanding missions want to go. The Hall thrusters are pictured in these photographs. On the top one is actually a picture of a 1500 watt device, and the plasma emanating from that thruster is clearly visible on there. It's a xenon-based plasma. It has a bluish tint, and if you buy an expensive Mercedes or BMW, that's the kind of headlight you're going to get with that kind of a bluish tint, because it's the same kind of plasma. It's a xenon-based light. Below it is a photograph of a 200 watt thruster, which is actually the first US thruster, Hall thruster, that has flown in space. And we are flying it now on a couple of different missions. Third one is about to launch later on this year. But the focus of today's presentations are these RF gridded ion thrusters. Ion thrusters or gridded ion thrusters have been around for a long, long time, since 50, 60 years ago. they have always run, or more in the last 40 years maybe, they have run on xenon and xenon alone, and they have been of the DC variety. Companies such as Boeing, that started under Hughes, is flying 2.2 kilowatts, 4.5 kilowatt thruster, gridded ion thruster fueled by xenon, which they call ZIPS, that stands for Xenon Ion Propulsion Systems. And just yesterday, they launched a Mexican-owned satellite that is all electric, propelled to its geospacecraft orbit by a larger device than this, which is DC ionized. And the companies, particularly Boeing, is pioneering this technology along with a company called SSL, Space Systems Loral, to basically make the launch of these spacecraft very much more affordable than if they had a conventional chemical propulsion. They make tremendous amount of savings by replacing the chemicals with the xenon propulsion, because then they can put on one rocket, one launch vehicle, 2 satellites, because of the mass savings in the propellant. So that's what's driving the technology in the larger sizes. But in our case, we focus on the small sizes where the DC ionization is replaced by RF ionization, and that's really our specialty. We build one that is 1 centimeter in diameter, and that's for very tiny spacecraft, CubeSat size. The one that you're gonna hear most about is 3 centimeters, about a little over an inch, and 7 centimeter, that's roughly 3 inches in diameter. And when I say the centimeters in diameter, I mean the grids through which the ions are extracted from the discharge chamber, not the external envelope. We also have a parallel program in order to companion program to the one that I showed you on the previous slide, which we call Lunar Cube, and that is an SBIR, and we are planning to send a 6U CubeSat to the moon using this particular thruster. So why iodine? Why are we switching away from xenon into iodine? Well, the primary reasons for doing that are the iodine is about 4 times as dense as compressed xenon, and it is stored as a solid, and therefore the tanks can be they can be made out of plastics, can be completely conformal, doesn't have to have a shape of a pressure vessel. And cost of xenon has been skyrocketing lately because of the aforementioned application in headlights. Xenon is now getting approved for application in medicine and in diagnostic equipment in Europe. And all of these things drive the cost of xenon to a level that is unheard of. And sort of the typical price these days for xenon is $30 a liter at standard pressure and temperature. So imagine a quart can filled with nothing, claim that there's a xenon, and you can pay $30 for it. To equip a spacecraft of the size that Boeing just launched with xenon, the price of xenon is probably $2-3 million to fuel the spacecraft. So cost is certainly one factor and not an insignificant factor in replacing xenon with iodine. But the primary reasons for the small spacecraft is the fact that small spacecraft are more volume constrained than mass constrained, and therefore the storage of iodine as a solid is extremely important. On these photographs, what you're looking at is the 3 centimeter thruster and running on iodine. And you can actually see the plasma glow from within the thruster through the ceramic enclosure. And that little blue dot in that picture is a source of electrons, which in this case is still blue because it is being run on xenon, not on iodine. And later on I will show you where this xenon is replaced with iodine, because we have now mastered the art of fueling these electron sources with iodine. Okay. All right. So what we were, of course, endeavoring from the beginning is to make the thrusters operable on both xenon and iodine. Xenon on the left, iodine on the right. You can see just by the color of the discharge what gas you're operating on. With the xenon, again, is nice and blue, sort of like the headlights. And the spectrum coming out of the iodine is a little tinted towards the yellow. So after a while, if you start running these thrusters, you can tell immediately just by watching the plume what substance are you running the plasma onto. So this kind of a system, in this case iodine, is what we are getting ready to put on the 6C lunar CubeSat to fly from GTO to the moon and enter the lunar orbit. On the next slide, there's some kind of a delayed reaction to this. I'm showing you what the performance is of that thruster that you saw in the previous picture in terms of power input versus thrust on iodine, and also thrust on the upper graph and ISP on the lower graph. And you can see that this device will put out at its nominal power around 60 watts, a little over 1 millinewton of thrust, which is more than adequate to perform a lunar mission, or even a mission that goes into heliocentric orbit, like I will show you later. The attractive features of these devices, whether they are fueled by xenon or whether they are fueled by iodine, is the very high ISP. ISP is a measure of the efficiency of the mass utilization. It's basically the thrust that you produce divided by the mass flow of the propellant you're feeding into the thruster. So a number like 3,000 seconds is about 10 times as high as you can get from the best chemical propellant, to put it in context. That is why electric propulsion is being pursued so heavily these days. On the next slide, I want to show you the rest of the components that go into making up a xenon RF ion propulsion system. The primary component actually is primary subsystem within the propulsion system is the power conditioning. And on this slide, you are looking at the power processing that's consisting of 4 boards. The most important board is the one that actually makes the RF to inductively couple it into the plasma and create out of an iodine vapor a plasma that then emanates out of the thruster and produces the thrust. So this board actually is quite tricky. We have achieved very high efficiency of conversion from DC to RF, and the picture on the side is just a standard neon light that we light up by placing the RF coil next to the xenon light to indicate easy indication of the working order of this board. Not the least of which is the high voltage board, which is around 1300 volts, and we have to start from roughly 13 volts. 3 to 12 volts on the CubeSat and convert it to 1200 volts, which of course is a challenge by itself. And all of that is accomplished in the stack of these boards that are going to be fitting into the CubeSat. This particular thruster this particular PPU, power processor, will fit roughly in 1U, a little less than 1U. It will process up to 120 or so watts. And the input, we are more focusing on the high end of the spectrum, because at 3 volts and 100 watts, the current gets extremely high, and we are not recommending to anybody to run a copper bus bar on their CubeSats. The overall efficiency for the PPU is 85%, which again is thanks to this very ingenious conversion from DC to RF. That has one additional feature, which is auto-tuning. The circuit is capable of sensing what the impedance of the plasma is and adjusting the frequency to make sure that the coupling from the RF side or from the RF coil into the plasma is the most efficient that one can achieve. Okay, here is the rest of the total system. On the left, you see the thruster itself. On the upper right, you see that power processor that we discussed a minute ago. Very importantly, here is the tiny little electron source called hollow cathode, this time running on iodine, and that's why you see the difference in the color of the plume. This is a technology that we are just mastering. It is utilizing an electron emitter that is basically a ceramic that is converted into, that is fooled by dopants to think that it's metal, and then without heating it, you can extract electrons out of it. And it's a very exciting technology that enables these thrusters to operate both the cathode and the thruster on the same substance, so you don't have to have 2 different tankages on the spacecraft. The iodine itself, when you order it from Alpha Acer, is a bunch of granules, metallic looking. You can put it in any conformal tank. This tank is made to go into the 6U CubeSats and hold about 1.5 kilograms of this iodine, or this metallic substance. And the distinctive feature of iodine is that when you put it inside a tank, all you have to do is heat the tank to around 70 to 80 degrees centigrade, and then the iodine goes directly from solid into vapor through a process of sublimation, generating enough of pressure, vapor pressure, to feed it directly into the thruster. So you don't need any compression, no high pressure tanks, no sort of demanding flow regulation. It just happens that the vapor pressure of iodine at 80 degrees C is just right to feed into the thruster and the cathode. So now I want to tell you a little bit about the applications for the missions that we are looking at. And this thing, I should credit a small company called Nextrack that helped us create these graphs. In this example, we are sending 6U CubeSat equipped with the 3 centimeter RF ion thruster running on iodine from GEO into a lunar orbit, and actually enter the orbit, because with this system can be 1.5 kilograms of propellant fitting approximately 2 U's, can deliver 12 kilogram spacecraft from GEO into lunar orbit, because it produces roughly 3 kilometers or 3.5 kilometers per second delta V. So without any special launch rockets, we can even start with a little bit less payload or a little more propellant. We can start at GTO, where rockets go regularly, about 30, 40 of them a year, and then go from GTO to lunar orbit and accomplish the same mission without requiring to go to GEO. That is a huge savings for any of the secondary payload missions that all of these CubeSats go onto. The next mission that in some ways is even more exciting is to go from Earth orbit, this is basically cislunar space, but we can go and enter sun-centric orbit and catch up with an asteroid that's going to fly by sometimes in October 2020 in the cislunar space between the Earth and the Moon. And starting again in GEO or GTO, we can spiral out, meet the trajectory of the asteroid, which is in the red barely visible out here, and co-fly with the asteroid so that you can, similar to the mission, to the Rosetta mission that the Europeans just did, co-fly with an asteroid. They co-flew with a comet and examine it with the appropriate spectroscopic instruments as to what that asteroid is, take a picture of it. And in some cases, if you are really, really clever, because the asteroid is small enough, doesn't have very big gravity, we could even attempt to land on it with the 6G CubeSat. So these are the primary exciting applications for this technology, and we certainly feel that the mission planners will, across the country and across the world, will take advantage of this capability and use this technology to do missions that were previously attainable only with huge spacecraft. So in conclusion, the BITS 3, which stands for BUSEC, ion thruster 3 centimeter, enables the very high delta V missions that I just described. I'll give you 2 examples of. People like not only NASA, but also people like Planetary Sciences that are intending to do prospecting of asteroids are very interested in these kinds of technologies because it will allow them to go and visit various asteroids, scout them out on the cheap. Iodine is really groundbreaking and game-changing because it allows you to put the propellant onto the 6G CubeSat in extremely dense state without having high-pressure tanks like Xenon would require 2,500 psi tank, and put it on that spacecraft because of its high density into a very small tank, which is at 0 pressure. That, incidentally, is a huge obstacle for many secondary payloads, because as soon as you want to put propulsion on a secondary payload, the primary payload says, you're not going to put anything pressurized under my spacecraft. And all kinds of red flags go up, and range safety starts asking questions about your safety factors, etc. Iodine avoids all these issues because it's at 0 pressure. NASA is supporting of this technology. We are actually going to fly something called ISAT with our Hall thruster, we're 200-watt Hall thruster, which pioneered the application of iodine in electric propulsion. And as the general awareness of these capabilities permeates the community, we certainly hope that the mission planners will take advantage of this capability. If we were to completely mature, get it to flight status, from this point onward, we feel that something of the order of $1 million will do it. We are anticipating further funding through the Super SBIR that NASA has coming up on phase 2, and that will cover most of this requirement of additional resources to get it near flight status. We do have all the facilities and all the talents to pull it off. And with that, I want to thank you and for your attention and take questions. Everybody understood everything. Yeah.
When you heat your tank for the iodine, what stops the back pressure from the air steam part? Do you know a valve?
Yes. There is a flow regulating valve in the line, but it's a very coarse, large orifice valve because of the low vapor pressure. The iodine just allows it to turn on and turn off. Any other? Okay, thank you.